Take sodium and chlorine. On the periodic table, these two elements sit in the same horizontal row, known as a period. Chlorine has 17 protons and 17 electrons, while sodium only has 11 of each. Physical intuition suggests that because chlorine contains more total matter, it should be the larger of the two, but the data shows the opposite. Sodium is the larger atom. Chlorine is significantly smaller, its structure compressed and held tightly toward the center. In our everyday world, adding more material to a container makes it grow. At the atomic scale, adding more matter can actually cause the structure to shrink. To solve this mystery, we have to look past the total number of particles and focus on how those electrons are arranged in the space around the nucleus. This arrangement creates an internal barrier called the shielding effect. Here, the inner shells of electrons act as physical blocks, preventing the outer layers from feeling the full strength of the nucleus. This invisible architecture is the primary mechanism that determines an atom's physical size and how much energy is required to remove its electrons. Imagine a rock concert where the positively charged nucleus is the lead singer on stage. A single valence electron is a fan standing in the very back row. The inner electron shells are like the rows of people standing between the singer and that fan, absorbing and blocking the sound before it can reach the back. This diagram illustrates that exact process. The inner electrons cast a shadow that blocks the positive pull of the nucleus, preventing it from reaching the outer edge. When an electron is caught in this atomic shadow, the nucleus has a weaker hold on it. This makes it easier to strip away. We can see this in action by looking down any vertical group on the table, starting at sodium and moving toward the bottom. Every step down a group adds a completely new, full shell of inner electrons to the atom. Compare sodium on the left to cesium on the right. While sodium only has a few inner layers, cesium has 6, creating a much deeper shadow over its outermost electron. Because the nucleus in cesium is buried behind so many layers, its ability to pull on the outer edge is almost entirely neutralized. This is why atoms at the bottom of the table have such low ionization energy. Their outer electrons are so heavily shielded that the nucleus cannot hold them securely. Now let's go back to the original mystery, moving horizontally across a period from sodium to chlorine. As we move to the right, we are adding electrons to the outermost shell, but we aren't adding any new inner shells. In this sodium atom, the 10 inner electrons form a fixed shield, casting a specific shadow. Even as we add more protons and outer electrons to reach chlorine, the inner blockers stay at 10. The shadow doesn't get deeper. Across a period, the atomic shield is locked. This lets the nucleus grow more powerful without any additional interference from the inner shells. Because the shield is constant, the nucleus is free to add more protons, increasing its positive charge from +11 to +17 without any extra pushback. We can calculate exactly how much of that pull reaches the outer shell using the formula for effective nuclear charge, the number of protons minus the shielding electrons. For sodium, the math is 11 minus 10. The gauge shows a net pull of +1, a weak grip on the valence shell. For chlorine, the math becomes 17 minus 10. The effective pull jumps to +7. The needle swings into the high-intensity zone. These calculations show that across a period, the increasing power of the nucleus completely overwhelms the static shield. We can see the result in this simulation. The high effective charge draws the outer shell inward, compressing the entire atom into a much tighter space. This resolves the paradox. Chlorine is smaller than sodium because its nucleus has 7 times the effective pull, allowing it to crush the atom's volume despite having more total mass. Ultimately, an element's size is not determined by the number of particles it has, but by the balance between the inward pull of its core and the protective shadows cast by its inner electrons.